Hey everyone, it's time to start talking a little bit about the statics we're going to do on rigid bodies. And so in this scenario, we're going to look at objects that have length, width, or height, so they'll have some actual dimension. So we might talk a little bit about the forces that are on this ruler, which might be at different locations. That's the idea behind the rigid body. We've taken anything, whether it was a car or some object hanging from the ceiling, like maybe a bucket. We haven't worried about the fact that it's got some dimension, some size to it, length and height, but now we're going to do that. Now we have to bring all of that into play. And so those are going to be considered rigid bodies or extended bodies. The term rigid is going to mean that they don't bend, like this ruler actually will bend, right? So you can see that bending, and we talked about this in the past. We'll talk about that more in mechanics of materials. But in this class, we're going to assume that it doesn't do any bending. But what happens now is when I apply a force to the ruler, if I push down over here, the ruler wants to rotate. All right, so when I apply a force at some distance from another point, whatever that point might be, it could be here at the end, could be over here. When I apply a force, I'm going to create what's referred to as a moment. All right, so this is called a moment, which is equal to a radius vector from the point of interest crossed with, so a vector cross product with the force that's being applied. In physics, we call this a torque, and we use the Greek letter tau in physics, right? So you might be used to this. That's the Greek letter tau. It's not the best tau on the planet, but that's the Greek letter tau, and we use that for torque in physics, but it's the same thing. It's the same thing. And so when we talk about a moment, we usually talk about a moment about some point. Oftentimes it's the origin, but let me just say some point A. And then R is going to be the radius vector or the position vector from A to where the force is applied. All right, so this is, I'm going to call it displacement to be more specific, because position implies that we are taking it around some origin. Oftentimes we do the moment about an origin, but it's going to be the displacement from A, that's the interesting point here, right, or the point of interest, to where the force is applied. Okay, so where F is applied. And that's going to give us the moment about A caused by this force. Right, so very specific. It's the moment caused by that force. If there's multiple forces acting around there, then that's going to be different. You're going to have different moments for all of those different forces, right? So if I had a force here and a force here, they're both applying a moment. Okay, then the other thing is that this is a cross product. Now, for most of this class, we're going to be working in two dimensions. And so what's going to happen is, let's say that this is my point of interest where my right hand is, and then I apply a downward force over here. That wants to rotate the ruler. Okay, that wants to rotate the ruler. So R goes from here to here, and then the force is down. And so if I point my fingers in the direction of R, and I rotate my hand in the direction of F, that's going to be into the board. That cross product is into the board. R cross F. R, rotate to F. Your thumb points in the direction of the moment. All right, so that's going to be, I like to do the curl on occasion, and I say to myself, what direction would the force want to rotate this ruler? And it's going to want to rotate it clockwise, and so I use the right hand rule, and my thumb points in the direction of the moment. If I push up on it, R cross F, I've got to rotate my hands this way, my thumb points towards the camera, that's going to be a counterclockwise moment, right? A counterclockwise moment. Now, one thing I didn't talk about, here's my circle for I, J's, and K's. Notice it's counterclockwise, my thumb points out, alphabetical, I, J, K. And so if I look at just unit vectors, I cross J gives me K, right? J cross K gives me I, K cross I gives me J. And then if I said K cross J goes to I, but I'm going in the wrong direction, so K cross J gives me negative I. Right? So you can use this to figure out what the direction of your cross product of two unit vectors would be. And we'll take a look at that in more detail later. All right, so let's take a look a little bit more at this whole concept of moments. So I want to use as an example opening and closing a door as a good example of moments, right? But I don't have a door, so I'm going to use this binder, right? And so the idea here is that I want to open the binder. I'm going to cause a rotation. I'm going to cause a rotation. And so if let me switch hands here. If I push towards the camera with my finger, I cause a rotation. R is the distance from the axis of rotation to where my force is applied. To where that force is applied. So the distance from the axis of rotation to where the force is applied. That's going to be R, then times the force that I'm using. It's not very much force because it's just a binder, right? Not a big deal. So there's R, then there's F. So R cross F points up. The axis of rotation is up, and it rotates. Use your right hand rule to curl. You can see the rotation then is in the direction that you're seeing. It's rotating it open. If I pull the other way, R cross F, the rotation is in the opposite direction, right? In that scenario, I'm closing it, right? So open, closed. If I were to push from over here with the same force, the moment will be less. Why? Because R is smaller. R is going to be smaller, right? So and then I'm pushing when my force is perpendicular to R. So R goes from the binder's spine to where I'm putting my finger, and then my finger points perpendicular to the cover. And so R cross F, everything's at 90 degrees, so the IJs and Ks are all in there, but the sine of 90 is 1, so I get maximum torque. I'm getting maximum moment. All right, so there's an example of a cross product. Now, when you open a door, try this sometime, open the door from the outside, it's easy to push. Open the door by pushing, let's say I was closing the door by pushing here versus here. This is going to require more force to open the door. And if you get really close to the hinges, it requires even more force to open the door. A good example of that is when you go to open a door and you push on the outside edge of the door, only you find out that's not the outside edge, that's the hinge edge, and it's very difficult, if not impossible. You probably don't get the door opened, or you come across a force required that you don't think you need. The other thing to take a look at is the whole idea of the cross product, and I'm going to hold this binder now like this. The idea is if my force is perpendicular to R, this opens up very nicely. Remember that the magnitude of the moment is equal to the magnitude of R times the magnitude of F times the sine of the angle in between R and F. Well, again, the sine of 90 degrees is 1. So when I go to open this binder, if my force is perpendicular, might be easier if I do it from this side. If my force is perpendicular to the radius vector, so the radius vector is along the binding, and then my force is perpendicular, I'm getting maximum moment there because my sine of 90 degrees is 1. But if I push, and I can push really hard, okay, I'm pushing hard on this binder and that's not opening. R is the same. R is the same. F is even bigger. But in this scenario, R is in this direction, F is in that direction. So R is, let's say, in the positive I, and F is in the negative I. They're at 180 degrees. The sine of 180 degrees is 0. And so what's happening here is I'm pushing hard, but the door doesn't open, the binder doesn't open. And that's because the angle in between the R vector, the position vector, and the force vector are at 180 degrees. Or if I pull, I don't open the binder when I'm pulling on it, because now R and F are parallel. The sine of 0 degrees is still 0. Okay, so where the force is applied makes a big difference. And then at what angle is the force applied also makes a big difference. All right, so that's a little bit of a lesson then on moments. Just go and open the door and push at different locations and then push at the edge of the door towards the hinges. and you'll see it doesn't open the way you think it would. All right. If you have any questions on moments, please be sure to leave them in the comments below. Thank you.